Thank you very much. Thank you to the organizers for having me come. Wonderful to see some friends I haven't seen for a long time and some new faces. So pleasure to be in Berlin as always. I don't know how you guys get any work done. If I was in Berlin, I would be doing, there's just so much beautiful stuff to do. All right, so I'm going to tell you about Lattice QCD inputs for neutrino-nuclei scattering. And I apologize, some of you are seeing this talk for the third time in 6 weeks. And I hope there'll be far less mistakes this time than there were in the previous time. So hopefully the talk is at least better organized. I'd like to start with saying thanks to the number of people we've worked with over the last 12 years in nucleon matrix elements. Thanks to the organizations which have given us computer time. And then in terms of just a general reference, there are 2 community papers which talk about the issue of what we need to do in order to provide the input from Lattice QCD, which phenomenologists need for neutrino-nucleus scattering analysis. Okay, so the talk's going to be highly subjective. I'm going to make maybe, hopefully not too outrageous statements, but what I believe, and then we can have a discussion. So I'm going to talk about what Lattice can provide, challenges, and then do some comparison of results, both with phenomenology or experiments and other Lattice calculations. As you all know, and I also am extremely grateful to Lorenzo, who provided a wonderful introduction to a large part of the talk. And I will use it shamelessly, and hopefully you were all awake during his talk so that you can make a connection between the two. So the experiments, neutrino oscillation experiments today span a region of up to about 5 GeV. And in this region, there is a number of different physics phenomena which take place. At very low energies, the neutrinos scatters quasi-elastically off nuclei. Then you have the resonance region where a struck nucleon can, the collective excitation of a pion, 2 pions can happen, and they can be sort of thrown out of the nuclei. And then as you go to higher energy, you have deep inelastic scattering, where the concept of just having a small perturbation of the nucleus breaks down. And that's usually done in, you can use perturbation theory at that stage, certainly above 4 GeV squared, where there is enough energy that perturbative calculation and factorization work. So we have to model this whole range. And at this point, most of the work which we are doing as lattice theorists is to look at the quasi-elastic region, the low energy region, and then hopefully over time we can even address the resident region. So the difference is that we want, in general, if we had infinite number of people working on it and infinite computer resources, we could program to start with an argon nucleus, put a current in it, and have some final state, and look at this form factor as a function of the momentum transfer. But this is certainly not going to happen in my lifetime. So we go to a smaller, limited goals step by step. So as I said, the first one is just the quasi-elastic, where a nucleon maintains its identity. You have just a transition from a neutron to a proton through the interaction of the weak current. Then, as I said, you can go to the resident region where you can talk about the nucleon going to a delta or a nucleon going to an n-pi. And then, of course, the deep inelastic scattering regime where this can be anything, can be multiple pions or stuff. So that's the hope. And the place where this then gets is that people take these lattice results and put them into a many-body Hamiltonian in nuclear many-body Hamiltonian, and then evolve that system to understand how to connect them to experiments. In particular, they put this calculation into event generators and therefore provide the whole basis for the analysis of experiments. Okay, so that's the outline of where we fit in and what the global large-term program is for neutrino nuclei scattering. All right, so let's start with the neutrino-nucleon scattering. Now, this can be described for both neutrino and antineutrino scattering in terms of a cross-section or a differential cross-section as a function of q squared, and in terms of three form factors, which are typically called A, B, and C, and the difference between neutrino and antineutrino comes in the sign of this term B. So these three form factors are written in terms of four form factors. The axial, F1 and F2 are the Pauli and Dirac electromagnetic form factors, and FP is the induced pseudoscalar. And this notation I'm using is the notation in the phenomenology community. And in most of the cases, I will basically revert to the lattice thing where we write it in terms of G. And the relation is, which I didn't have it, is that there is a relative minus sign in the definition between G and F, between what phenomenologists use and what we use. Okay, but the basic idea is there are these four form factors, which if you were to do everything from first principles, you need to calculate. Okay, so to this list, I will add a fifth one, which is just the pseudoscalar form factor, which is extracted by putting the pseudoscalar density as an operator between the nucleon states, whereas here you are doing it by putting either the vector current for the first two cases and the axial current for the next two. So these are the five form factors, and the reason we want to calculate this fifth one is that these three form factors are related through the axial Ward identity. And this, I will emphasize, is an extremely important check that all calculations have to satisfy, that the form factors satisfy the axial relationship. We also have very good experimental data on the values of these form factors at q squared equal to 0. For example, charge conservation says that the electric charge is 1 at q squared equal to 0 magnetic from the magnetic moment. We have measured the axial charge extremely well, and we also have a good estimate of the induced pseudoscalar charge defined at this particular scale, which has to do with the muonic atom in which it is measured. So we have the form factors, we have the constraints, and so now we move on to doing the lattice calculation. In terms of the lattice calculation, what we need are 2-point and 3-point functions. We know how to do this extremely well, and we also know how, from rigorous first principle, how to analyze the data. So you do a spectral decomposition of the 2-point function, and that spectral decomposition gives you the spectrum and the amplitudes for the creation or annihilation of the nucleon state, within which then, in the 3-point function, you measure the impact of an operator. The difference here is this is the amplitudes and the energy, and here you also get the matrix elements in the transition from one nucleon state to the other, and the sum is over all possible internal states allowed by the particular, by the transfer matrix, but starting with the states which are created by the interpolating operator. Okay, any questions so far? So this lattice methodology is very well known. There is no controversy. Okay, so the problem to a large extent, which I will spend a fair amount of time, is understanding what are the excited states which contribute in this sum, and how do you get rid of all the excited states, because eventually what you want is the transition, is the matrix element between ground state to ground state. However, what the lattice gives you is that at any given time in between, you have the wave function, which is the full Fock state wave function of the hadron which you have created using your interpolating operator. Now, this is true in all correlation functions, but it becomes a problem in nucleons because of two reasons. First is that there is a huge number of excited states which are low-lying comparatively to, say, mesons, and they typically start at about 1200 MeV, which is about just 300 MeV above the nucleon itself. And you can see that as you make a lattice larger, which is what you want to do, the spectrum becomes finer, and therefore you have an increasingly dense spectrum of states, which you have to then take care of and get rid of them. And this remains a challenge and is certainly something which is something which people can work on. So it's a challenge to the next generation. Okay. And Lorenzo showed us his response, the next generation's response to doing that calculation. So what are the other challenges which I will emphasize? First is the nucleons have a second problem, that the signal to noise degrades as you take the separation between the source and the sink. So the typical method for isolating excited states, which is to let the system evolve for long enough time, fails. And at this point, the best calculations, the signal in the 2-point function and the signal in the 3-point function extends to about 2 Fermi, 1.5 Fermi, and as you make the correlation function more and more insertions, this distance decreases. Second, as I've said, that there are whole towers of excited states, these multi-hadron states. And the second part is, corollary to that is because the difference in the mass gaps between, say, an n-pi state and the Roper, this difference really starts to play a role when the light quark mass or the pion mass becomes roughly less than 200 MeV. Because as you have a heavy pion, the difference between a Roper and an n-pi state is not very large, and therefore you really can't distinguish the thing. Actually, there's something I want to, point out. The other thing I want to point out that when you're looking at a 3-point function, what you get are these products of amplitudes and this matrix element, and it turns out that all you need is the ground state amplitude. The other ones, you get this combination, and all you're doing is removing it in the fit. And that's the goal. You don't care individually about amplitudes and matrix elements. You just care that there is this one product unknown which you want to eliminate. Okay. So that's the challenge. And how do you know what states contribute? And there, chiral perturbation theory has turned out to be a really good guide. And actually, I will try and convince you that we've known about all the cases, or almost all the cases I know of, for the last 60 years. They just had different names. All right. So this now is work which was started by Oliver, where is to understand what chi-pt tells you. So there are two things I want to emphasize. First is there is a normal pion loop which impacts all correlation functions, all 3-point functions. So this is there. And the question is at what level? So one has to always start and say this chiral loop is there, and when you do chiral perturbation theory, your corrections, your nonlinear corrections, your m-pi cube terms, your logs and everything, you know it's there because that's what you take care of. That's what chiral perturbation theory gives you. But there are also excited states which arise, or the contamination, when the pion comes on shell, and that you have to remove. So what Oliver pointed out is if you look at the axial current, then it can connect to a pion, And that pion, if it's part of your initial interpolating operator, that your interpolating operator is actually creating not just a nucleon, but a nucleon and a pion, then this gets, is not suppressed, and it plays a large role. This, for last 60 years or 70 years, has been known as pion-pole dominance. So I'm just connecting things which we've known for a long time with the modern language so that you don't say, oh, but is it really true? No, we've known about it for 60 years, 70 years. The same thing, oops, I keep pressing the wrong. The same thing is true if you look at this scale vector channel. This is the vector meson dominance, that the vector current couples to two pions, and there is an enhancement, but that enhancement is much smaller than the case of axial, simply because the vector meson is heavier, amongst other things, and also the coupling is smaller. The same thing happens in the case of the scalar, and in the case of the scalar, in addition, you can see that disconnected diagrams will have a much larger contribution because a scalar current coupling gives rise to this n-pi state very naturally. And the other thing you can regard is that we know the condensate is large. That's the language in which we had first learned about why the scalar channel should be large, was we know that the quark condensate is large, and so it manifests itself in saying that the scalar matrix element is going to be large. So we've known this forever, and now we are doing it in the modern language of chiral perturbation theory. Any questions on that? Or the one thing which I haven't talked about is the same thing applies in the case of CP violation, where we've known again for a long time that G0, which is the pion-nucleon coupling, is large. And that again feeds back into when we are looking at CP violating operator like the theta term, that you again expect there to have an enhancement due to these n-pi state. So sorry, that thing is not there because I was sticking to CP conserving calculations. All right, any questions on the motivation for why we expect enhancement on these cases? Okay, let me then move on. What have I done? All right, so then the next thing is that typically what you say is that the axial current couples directly to the nucleon. That's your axial charge. It couples, but then it has a form factor because you can see that if you strike one of the quarks, which is what our standard model tells us, the axial current couples to quarks, then if you strike a quark, it moves because you've transferred momentum. In the end, then for the nucleon to stay a nucleon, somehow that transmission of energy momentum has to flow to all the three quarks. And this is the physical picture why the form factor should fall off at large Q squared as 1 over Q to the fourth. So you get 1 over Q squared from each of these gluon exchanges. The pion-pole dominance is that the axial current couples to the pion, and then the pion, being light, has a pole, which then couples through the G pi NN coupling. And in this case, we are just looking at the CP conserving. The CP odd part of it has an expansion in terms of parameters like G0, G1. And as I mentioned, G0 is enhanced. Okay, so the next thing is that once you have the ground state matrix elements, only then can you decompose the form factors in terms of, or the matrix element in terms of form factors. Otherwise, you will have more terms. So this is also in terms of, in the isospin symmetric limit, otherwise you have yet another term, the induced tensor, but I've dropped it assuming isospin. So you can now decompose it, and therefore remember, these are the two things which experimentalists want. Similarly, the pseudoscalar has a decomposition in terms of the pseudoscalar form factor. And PCAC, which is the divergence of the axial current, relates these three. All right. So that is constraint one. Then also when you're doing numerics, the same thing also tells you that you can look at correlation functions, and if you look at the fourth component of the axial current, that the derivative, you can calculate that on the lattice, and you can calculate this quantity on the lattice, and these two, again, need to agree. And the third point which I want to make is that you have an overdetermined set of form factors or currents, and I will emphasize this, that there are two ways in which you can extract these form factors, or two combinations, and they have to be consistent. All right, so let's talk about that. So you have four components of the axial current, and you have only two form factors, which is the axial form factor and the induced pseudoscalar. So in the case of I'm putting the spin projection in the three direction, which picks a certain preferred direction. So 1 and 2 basically give contribution only to the induced pseudoscalar. And so that there is no contamination and stuff. The next two have a linear combination. If you take Q3 equal to 0, which is what you can do in the forward direction also, you get directly GA. If you take a non-zero component in the three direction, then you get a combination of the axial form factor and the induced pseudoscalar. Similarly, in the case of the A4, you get something which is proportional to Q3, and as long as you have momentum in the three direction, you can then get a linear combination of your inductance. Now, people have made cases that, okay, I can worry about this and worry about the fact that there is enhancement and in my extraction of the induced pseudoscalar, because that has the pi and pole dominance. But when I'm doing my analysis of the axial, I can work in a region where Q3 is 0, so I can get that, and I don't particularly need to worry about n pi, or I can do that. But on the other hand, forget this. I could just totally ignore this line. If I had precise data, I could easily get both form factors from the first and the third. Remember, excited states have to be removed at the level of the correlation function and not the form factors. So if I want to just do the calculation using the first and the third equation, then in both cases, now I have to include n pi. I cannot here make the claim that, oh, I can separate the two by choosing momentum. Here, I am bound to do the calculation including the n pi, or all the slew of excited states. So this is the case we've made of why you need to include the n pi state in the analysis, whether it's axial or induced pseudoscalar form factor. So here, a little bit more detail on what Oliver did, which is the same picture. You have the axial current coupling to the pion, goes to the nucleon. Now, typically, the nucleon pion state, if it creates that is relatively suppressed to just the nucleon by a factor of 1 over the volume. That's the amplitude. But now you come to the fact that this axial current, converting into a pion, because the pion is light, can happen anywhere on this time slice where you're doing the current insertion. So you get a volume enhancement by a factor of V. And because of these cancellation between the state initially produced by the nucleon and the fact that you have this volume where the interaction can take place, you do not get a suppression. This matrix element is large. So that is the basic physical picture which Oliver provided us with. And then he did, to sort of show that, yes, it was true, he took a lattice data and showed if he fixed it or massaged it, he was getting a much better estimate for the induced pseudoscalar. But what we were doing was that if you now look at that A4, now that A4 has large excited states. This was known right from the very beginning. But the signal was bad, and people basically threw it away. They said, look, we can get all the form factors we want from the first three components of the axial current. This thing is a problem. Why bother with it? Throw it away. So, sorry, why do I keep doing this? Why won't it go back? Yes. So we actually did a fit to this and realized that the original fit is very bad if we don't include the NPi, and it improves very significantly when you include the NPi. So this was a data-driven. Even if Oliver was not around and we had done this analysis, data would have been telling us that you can't get away without the NPi state. Putting in the NPi state is totally sort of demanded by the data. So this is where our realization comes from, that you need the NPi state, and it's totally data-driven. So to summarize, in 2017, when we were playing around, we realized that PCAC, the old way of doing it, was not satisfied. And then once we put in the NPi state, we found that the relationship gets satisfied, and that was shown in our paper, that there was almost a factor of 2 deviation, which then comes to within 5 or 10%, which we can assume based on discretization, which is allowed even for a word identity. And the second thing we noticed was that PCAC, and if PCAC satisfies, pi and pole dominance also is satisfied, they basically track each other, and that has remained the case ever since. Okay, so now again the physical picture. What we want is the ground state matrix element. The current inserts momentum q, so a nucleon with momentum 0, because we have fixed this to be 0, goes to a nucleon with momentum q. That's what we want. But then you can easily convince yourself the same quantum numbers. You can have 2 possible excited states, transitions, and those have to be removed. The other thing, when we did this analysis, we also showed that the spectrum you get on the 2 sides, which is different because of momenta, is actually done, is being explained by the fact that there is a NPi state, as contrast to these black points, which would be the case without having the NPi. And this also shows you that it's really, when you come down to small momenta and lighter pion masses, that the difference between the 2 ways of doing the analysis of your spectral decomposition becomes important. Okay, so here is an example. The problem is that in many of these cases, the fits are not very different, but the extrapolated value is very different whether or not you include the NPi state. And overall, today I would say that at least our analysis, why am I doing this? Our analysis says that the uncertainty in the axial, which is just coming from the loop uncertainty, there's no enhancement, is of the order of 5%, but in the induced pseudoscalar and pseudoscalar, it's about 35%. So it's a big deal. We have to get rid of it. Okay, so now let me just summarize what are the essential steps in doing the analysis. There are 5. First and foremost, you have to remove excited states. If you don't remove excited states, you can't do the decomposition, and therefore, end of story. Then once you've remove the excited states, you decompose the matrix element into form factors on each ensemble. Now you have a function of q squared. So the next 3 steps have different ways. People can do it in different ways. There are some who choose to parameterize this on each ensemble, then extrapolate to the continuum value, and then reparameterize this form factor in the continuum to give you your final form factor, which can be used by experiments. Others choose to do some combinations, and this is where the analysis will become more involved, taking into account how different people choose to do that. But basically, I've written the 5 steps, which are the most sort of intuitive or naive, and that's what we typically use in order to do the extrapolation to get the continuum value. So if you're doing model averaging, at each stage you can make a model of how to parameterize, how to decompose, how to perform this extrapolation and stuff. So if you want to do model averaging, then at each stage you have to take into account the models and in the end include the model averaging. Now the problem, as I told you, that data is agnostic. If you look at it, chi-squared by itself is not sufficient to tell you what the excited states are for many of these correlation functions. You can have the first, you can have that the Roper, if you put that in as the first excited state in your spectral function, or you put an n pi, you get roughly the same chi-squared. So there's a flat direction in chi-squared, and therefore you have a problem in terms of model averaging. And what we've done is to take two extreme cases, because there's nothing lower than that, and this is typical. So that provides a way of doing model averaging. The other thing is that another consistency check is that you can calculate the matrix element in the forward direction, which is your charge, in two ways. One, you can calculate it, in two ways. One is you calculate it in the forward direction, end of story, or you can take your form factor as a function of q squared and extrapolate it to q squared equal to 0. So in some sense, I mean, they are not different, but you can do it in two different ways, and they should be consistent. And you find roughly that that is the case up to within the errors. But you know that this form factor, when you extrapolate, the set of three form factors do not satisfy PCAC. Now, on the other hand, if you took this with n pi, the GP twiddle and the GP and GA without it, because this is about a 5% change, you can satisfy PCAC to that 5-10%, and you can say, oh, GA doesn't need to be analyzed with n pi, but as I explained to you, I don't believe that's the correct strategy. Now, if you analyze it where you put n pi, then you get consistency, but you get a larger result, and that is the conundrum which we face today. How do we make sure that we can validate this with data? And I think as we get more data, we'll be able to do that. Okay, so this is a busy slide. I'm just going to leave it. I just put down my version of how 5 collaborations have analyzed using those 5 steps. What have they done for parametrizing the form factor and then extrapolating and stuff, and you can take a look at it and stuff. But the nice thing, it's actually emerging, is there is a consensus. So those 5 calculations, if I plot them, this is the overall band of the results from those 5 calculations. Here, we've compared them to each individual one, and you can see that our magenta and the Regensburg group are pretty much overlapping. This was their form factor, which is not parameterized, but it's there. And then ETMC, which was based on one physical mass, our 2+1 Clover, the mines were. So basically, you start to see a consensus emerging. There's a little bit of difference with the mines, but their error bar is very large. So you get a value for GA, you get a value for the axial radius, and the consensus is that as we improve this, will work. Now, the big thing here is the difference from the previous benchmark result, which was the analysis of the neutrino-deuterium data, and that gives a form factor which in the small q squared region pretty much agrees, or the lattice agrees, or whichever way you want to say it, with it, but certainly at large q squared, we are beginning to see a difference. So what does this mean for phenomenology? Recently, Minerva came up with a very clever way of actually isolating the contribution of the nucleon form factor by looking at scattering of a hydrocarbon target. And so the points are their data. The red is what I took from those representative form factors. Our calculation is the result you would get for the cross-section, the differential cross-section. And then the black is the deuterium fit. And you can see that in the small q squared region, the experiments will not become precise enough to give us the form factor. In the intermediate region, what you see is that at least the consensus form factor lies in between the Minerva data and the neutrino-deuterium data. And then at large q squared is where the lattice errors grow. So the biggest opportunity for lattice, which is where it happens to be proceeding normally or naturally as you increase the lattice size and decrease the lattice spacing, is the small q-squared region. So this is going to be our biggest area of impact. And here we will be refining to see how exactly this plays out. But this is a very exciting possibility or future that we now can actually sort of have an impact on phenomenology. And we know exactly the regions in which we have an advantage versus experiments. Yep. Okay, so we've mapped this. We've broken it up into 3 regions. As I've already told you, the region of small q-squared is where we have the max advantage. And I think by and large by now, the neutrino deuterium data will slowly and steadily lose its benchmark status, and people will become more and more working with either experimental output like from Minerva or the lattice calculation. Okay, so I just want to now see there were some unpublished results at the Lattice conference. So the thing which is, you could ask, why is there a consensus emerging when you have so many different ways of doing the analysis? And what is true is that most of these form factors we are finding do not have large dependence on either the quark mass or the lattice spacing. And as a result, the errors which you get are reasonable. So here I'm showing you the ETMC, which have now gone from 1 ensemble to 3. And you can see the difference is that a tiny bit, it moves up a little bit, but within the errors. The other thing, they've done an analysis of their breaking of PCAC, and they are claiming that it has 2 factors to it. One, which is maybe the n-pi state, but a large part of it is coming from discretization errors, which they say that arise because twisted mass formulation does not treat pions well, and that is leading to their thing. So we will see how this evolves. And also, when they do an analysis of the A4 state, they now are seeing that they can find the n-pi state as contributing. So that part is also consistent with the picture I explained to you before. Okay? There is one lattice calculation from the CalLat, but that also pretty much, as you can see, follows the behavior, which is, as I said, the consensus, or in this case, the lattice, which I already talked about. Here is an update from our calculation. We had done this with Clover fermions on 7 ensembles. We've now extended it to 12 here. And you can see that variation with pion mass or lattice spacing is small. And this is, I think, a good situation where we are all seeing that this variation is small, and therefore the extrapolations, how you do those 5 steps of the calculation is not as important, because if you have data which is not very highly varying, then any method will basically give you a consistent result. So that's a very good situation. Okay, then I'm not going to say very much. There is results which are coming from PAX, the Japanese collaboration, which is using very large lattices, but with very few configurations. And they have some results which look very good, some which don't look very good. But I think over time, hopefully, they will get all of this together. And my sort of request to them is to improve the statistics. They are much more caught up in the fact that they're doing a master field. No, they're not doing a master field. If you have only 20 configurations, and you cannot even guarantee a correlation length of time, but that's their call. So, okay. Similarly, there's from RBC, which was results given by Shigami, and again, I don't fully understand them, but I'm waiting for them to write it up to see what they find. All right. So net result is the places where new results are coming, like ETMC or CalLat. you're finding again the consistency with that picture I showed you of a consensus. The others two, we will wait and see how they evolve. So again, an excellent situation. Oops. I'm almost done. The same story with electric and magnetic form factors. We find extremely good agreement with the Kelly parametrization of the experimental data and very little dependence on the pion mass or the lattice spacing. In this case, if we plot it as a function of q squared over mn squared, but we are free to choose what variable. It depends on where we can minimize the errors or the spread, because in the end we can take a continuum limit either as a function of q squared or q squared over mn squared. Okay? The last one, which I'm not going to cover much because this was Lorenzo. He talked about a lot of the starting of the calculations of actually going from n to n pi, n plus n pi. And that's the variational approach he talked about. And there's a fantastic, it's great to see the thing. And hopefully, over time, it's not just to demonstrate that n pi is a state which you can actually validate by doing this direct calculation, but to actually start calculating these transition matrix elements. So with that, I will end. Looking forward, we have a problem, which is still a problem, and there are ideas of how to reduce the signal to noise through generating ensembles very cheaply, through normalizing flows, to removing the noise, which is coming from the phase, through doing contour deformation. So there are ideas, but realizing them is next generation's task. We need to continuously develop our analysis strategy. I think we understand the calculation, we understand the decomposition and the spectral decomposition and the how to do it. And now, as our data improves, many of those things will get resolved. Our current best hope is that within this region, we will give results of use value to experiments. For higher q squared, we need to work on methods to improve them. There's the momentum source methods, which we need to really pin down so that we can provide the form factor over the whole range, the transition matrix elements. So in the end, the golden sort of holy grail is to get all these form factors from first principles so that there is no, that's what we want to do and provide them for the analysis in experiments. So thank you very much.